we're going to work our way to talking about logistic regression, odds ratios, and how we can adjust for confounding and so on. Before we get there, we need to remind ourselves a bit about multiple linear regression. What is the model? What's it used for? The goals of regression models, what's confounding and effect modification, and so on. Okay, so we want to remind ourselves of some of those concepts before we build on top of those. Okay, and the reason for doing this is logistic regression is very similar to linear regression. Okay, so we can use the understanding that we're building for linear regression to help us understand logistics. Same with the idea of confounding. A confounder is a confounder regardless of the type of regression model we're using. Same with effect modification. A quick reminder that multiple linear regression, well, we can think of it as an extension of simple linear regression, just including multiple x variables. This is used when our y, our outcome, is a numeric variable, and the x or explanatory variables might be numeric and or categorical, okay, or a mixture of both. So here we're modeling the mean of y as a linear function of the x variables. A few examples that we've worked with or are going to work with. The first one was looking at the relationship between FEV or lung capacity and x1 being smoking, yes or no. And we may want to include other variables like the child's age, their biological sex, and their height. The second example we're going to talk about a little bit in this discussion is looking at the relationship between body fat percentage, so the y variable is body fat percentage, and trying to estimate body fat percentage using BMI, ab wrist circumference, which is the ab circumference minus the wrist circumference, as well as the age categorized into age decades, I believe. A reminder that when fitting a regression model, we need to have some research question or some goal in mind. And for the most part, we can place our goal into one of two broad categories. We might be looking at building a predictive model or an effect size model. So a predictive model, there the goal is to build a model that's good at predicting the outcome. Okay, and we don't put much emphasis on interpreting the coefficients or the effects of certain variables on the outcome. Thinking of that example 2 data set, we might want to try and estimate what is someone's body fat percentage, which is somewhat difficult to measure, using variables that are simpler to measure. So can we use someone's BMI, which just requires a measuring tape and a scale, right, or their ab circumference, or their age, or other variables to try and estimate what is someone's body fat percentage. So that's a predictive model. An effect size model is where we want to estimate what effect does some variable x1 have on the outcome while controlling for other variables, which may be confounders or effect modifiers. So there, our goal would be to estimate what effect does x have on y. So in those example data sets, what effect does smoking have on someone's lung capacity? Does it lower it? And if so, by how much? Using that second example, the body fat percentage, we might want to estimate something like if someone exercises for 30 minutes a day, 2 times a week, what effect does that have on their body fat percentage? Does it decrease it? And if so, by how much? And then we might need to think of what are potential confounding variables and adjust for those. The approach to building a model and selecting variables that should go in it really depends on, are we trying to predict the outcome, or are we trying to estimate the effect that some variable has on the outcome? So just to build on that, when we're looking at an effect size model where we want to estimate what effect does x have on y, we're trying to estimate the effect of some variable on the outcome, it's really important for us to identify variables that are confounders, right? So variables that are associated with our x variable of interest and associated with the outcome. Okay, we need to identify those and control or adjust for them in some way. If there's any variable that's collinear with our variable of interest, so essentially that's a variable that's another measure of our variable of interest, we want to remove those from our model. And we want to think of anything that's potentially an effect modifier and include that in our model. If we're building a predictive model, our goal is really to try and predict or estimate the outcome. The focus of which variables should go in or should not go into the model really involve including variables that increase the predictive power. So if something is associated with the outcome, it's a good predictor of the outcome, then we want to include that in the model. And it's also important that any variables that we're going to put in our predictive model are going to be available at the time of prediction. Okay, so when we want to be able to make the prediction, can we have those measurements recorded at that time? And we want things that are easily and reliably measured, so that things that are not subjective measurements. So here we've got an example that I'd like you to take a moment to try and think through. So let's imagine your outcome variable is y. Right? Does someone have a heart attack before age 50? Yes or no? I want you to think about what is a predictive model in this context. Okay, what's the question that's being asked, and which variables might you consider including in this model? And then I want you to think about an effect size model in the same context with the same outcome variable. What is a question that you might think of asking, and which x variables might you consider including in it? I'll give you a few seconds to think about this, or you might want to pause the video and think about it, and then I'm going to shout out some answers or some things to think about. Okay, so first let's think a little bit about predictive modeling. Here, our goal is really just to estimate what is the probability someone will have a heart attack before the age 50. And we want to think about which variables are going to be good at predicting this. Some that I've thought of, and I'm sure you can think of more, maybe some better ones, but things like what's the person's age? Right, that is probably going to be predictive of whether or not they're at risk of having a heart attack before 50. Biological sex, maybe. I believe males are more likely to have heart attacks than females, although I can be corrected on that if that was wrong. Things like, do you have a family history? Has someone in your family had a heart attack before the age of 50? Smoking, your diet, and other risk factors for a heart attack are going to be good at predicting whether or not that will happen before the age of 50. Now, thinking of an effect size model, here the questions we want to ask is, what effect does some variable have on that risk? One we might think of is treatment A versus treatment B. Is one treatment more effective in reducing that risk? Or we might want to ask the question, what effect does smoking have on your risk of having a heart attack before 50? Does it increase your risk? And if so, by how much? Does it double your risk? Does it triple your risk? Does it increase your risk but only by 5%? So these are the kind of questions we want to answer there. And in doing so, we're going to want to try and identify what variables are potentially confounders. Okay, so what variables are both associated with smoking and associated with a heart attack before the age of 50. One variable that may potentially be a confounder is age. There we're thinking that age is associated with your risk of heart attack. Right? As people are older, there's a higher likelihood of them having a heart attack. There we're also thinking that age is associated with smoking. Are smokers older on average than non-smokers? Okay? Or if smokers are on average the same age as non-smokers, there is no association. Okay, so here I'm hypothesizing that younger people are less likely to smoke, older people are more likely to smoke. This may or may not be the case, and we could check data to see if that seems to be true. Another potential confounder might be something like exercise. Is regular exercise associated with risk of heart attack? Okay, it probably is. Exercising probably reduces that risk. And we're also thinking here, is exercise associated with smoking? Here I'm hypothesizing that people who smoke might be less likely to exercise than people who don't. If there is no association between exercise and smoking, then this variable is not a confounder. Okay, so what I'm trying to lay the foundation for here is that the variables we think about including in a predictive model versus in an effect size model are a bit different. In effect size models, we're really asking what effect does one variable have on the outcome, and we want to adjust for any variables that are potentially confounders. Predictive models, we're just focusing on which variables are good at predicting the outcome. So this slide here is just summing up some of the things we were just talking about in terms of selecting variables for effect size models. So let's recap a little bit the idea of confounding. We already explored this in our first meeting, but we're going to discuss it a bit further and remind ourselves of these ideas. Here, we're interested in estimating what effect does some variable x1 have on some outcome y. Okay, or here in this diagram, what effect does the exposure have on some outcome? And confounding occurs when this other variable x2, which is labeled here as a confounder, is both associated with our exposure of interest and with our outcome of interest. Okay, so this confounder both has an effect on the outcome and has an effect on the exposure or some association with it. The notation we're using here is x1 is our variable of interest, and we want to know what effect does x1 have on y, the outcome. x2 is the other variable, the confounder. So for a variable to be a confounder, x1 and x2 should be associated, and x2 should not be on the pathway between x1 and y. So this was what gets called mediation. So this would be if x1 leads to x2, which then leads to y. Okay, x2 is sitting on the pathway between x1 and y, or sitting in the middle or mediating that relationship. Okay, so for a confounder, x2 should be associated with x1, but not having x1 causing x2. x2 is also associated with y, or the outcome. Then what we'll see numerically is if we include x2 in a regression model, if we adjust for that confounder, the estimated effect of x1 should change. The variable should make sense conceptually or biologically as a confounder. So we'll take a look at a few examples and see if these make sense conceptually. The first example is where our question of interest is what effect does smoking have on someone's risk of lung cancer? Now, there may be another variable like occupation. What occupation does someone do? And this may be a confounder. If this variable is a confounder, what that means is occupation has an effect on lung cancer. To simplify the example, we're going to think of smoking, yes or no, lung cancer, yes or no, and occupation, I'm going to simplify it for the sake of our discussion. Let's think of, is someone working in construction or not? Okay, so are they working in construction or in some other occupation? And again, I'm just simplifying it to two categories to make it simpler for us to think about. We want to think about, does occupation have an effect on your risk of lung cancer? And here we're thinking of occupation, working in construction, yes or no. What we're thinking here is someone who's working in construction outside, let's say working on building a house or building a new high-rise, something like that, they may be at an increased risk of lung cancer. So they may be out there outside working, exposed to a lot of dirt or concrete being grinded, things like these, things that they're breathing in and increasing the risk of lung cancer. Then we also want to think for occupation to be a confounder, it should also be associated with smoking. Here we're thinking, does the likelihood of you smoking change depending on your occupation? Okay, and again here, we can think it's quite reasonable to assume that there might be an association. So someone who's working in construction, we're going to assume is more likely to smoke than someone who's not. And this could be for a variety of reasons. Maybe because they're working outside most of the day and they have more opportunity to smoke. Maybe the type of job is just associated with people who are more likely to smoke than other occupations. Here we're saying occupation conceptually seems to fit the bill as a confounder. And then I guess the final thing to think about is to make sure occupation is not on the pathway between smoking and lung cancer. So here we're thinking, does smoking directly affect your occupation? And no, it shouldn't, right? Smoking or not smoking shouldn't have a causal effect on what your occupation is. Let's take a look at another example. This is one we talked about in our previous meeting. Suppose we want to look at what effect does the amount of time you spend studying have on the grade you get in this course. Okay, so that's our question of interest. And we've identified a potential confounding variable as your prior knowledge of statistics. So we want to think here again, is prior knowledge a confounder? In order for it to be a confounder, we'd have to think about, does prior knowledge have effect on the grade you get in this course? And yes, it should, right? If you've taken lots of stats courses and you know a lot more, you're more likely to get a higher grade in this course than not. Then the second thing we want to think about is prior stats knowledge and study time associated? And again, they probably are. If you already know this material pretty well, you're probably going to spend less time studying or need to spend less time studying. And then we want to make sure that prior knowledge is not on the pathway between study time and stats grade. Okay, so here we're thinking, does the amount of time you study directly impact your prior knowledge? And no, it doesn't, right? The amount of time you're studying now cannot affect how much stats knowledge did you have before entering this course. Okay, so it's not meeting the criteria as a mediator. It seems conceptually to fit as a confounder. Effect modification. So we'd like to take a moment again to remind ourselves of what is effect modification, what does it mean, what are its interpretations, and so on. And so again, this is something we talked a bit about at the end of our first meeting, and now we're going to recap it and build on it a bit more. Effect modification essentially is where we want to say what effect does some variable x1 have on some outcome y. And there's this other variable x2, okay, the effect modifier, that modifies or changes that effect. The effect that x1 has on the outcome y changes depending on the values of x2. I know that this is a little bit generic right now. In a moment, we're going to get to looking at a few examples to try and discuss exactly what this would mean. The effect modifier should make sense conceptually or biologically. In health research, some of the more common effect modifiers are biological sex, age, or race. Okay, so if we're thinking, what effect does exposure have on some health outcome? Not always, but often, the effect that an exposure has on some outcome might be different for males and females. Okay, the exposure might be more harmful for one than the other. Or age is a very common effect modifier. The effect that exposure has on some health outcome might change depending on if someone is middle-aged or very old. So again, age may be a modifier. And a final common one is race. So again, the effect of some exposure has on some health outcome may change or may depend on someone's race. So let's take a look at a few examples and discuss these a bit more. So the first example we'll look at is supposing we want to estimate what effect does the time spent in the sun, let's say without sunscreen on, have on the risk of skin cancer. So every additional hour you spend in the sun, what does that do to your risk of skin cancer? Okay, now here, race is quite potentially an effect modifier, meaning the effect, say, of spending 1 hour in the sun, the effect that that has on your risk of skin cancer might change depending on someone's race category. Okay, and the thought here is that an hour spent in the sun may be more harmful for some than for others. Here we're thinking of race as being a proxy measure for skin tone. Okay, we know that the lighter skin is, the more sensitive they are to sun, or the more damaging an hour spent in the sun is. The darker the skin tone, the less sensitive to sun. The effect of spending 1 hour in the sun without sunscreen, it may be more harmful for someone with lighter skin than with darker skin. Okay, so here's an example of a potential effect modifier. Here's a second example we can think of, and this is one that you've worked through on the assignment. So there, you're working through this idea of, say, comparing the effect of sex on salary. And so the context was looking at salaries within the university. Okay, and you might want to see, is there a difference between the average salary paid to a male and a female? Salary discrimination based on sex. And here, a potential effect modifier could be the faculty that someone is in. So let's just think of medicine, business, arts, and science. If the faculty is an effect modifier, what this means is the difference between the average salary for a male and a female changes depending on the faculty they're in. Maybe, say, we'll just make up some stuff for the sake of the discussion. Suppose that in business faculty, there's a very big gap between males and females. Within arts, that gap is quite small. Within science, it's a medium-sized gap. So again, this is effect modification. The effect that sex has on salary, okay, or the difference in the mean salary of a male versus a female, changes depending on which faculty they're in. I want you to take a little bit of time to think through these, and I'll come back once I've given you some time to think and give you some of my answers or some thoughts. So here we want to try and think about estimating what effect does diet have on the risk of diabetes. Okay, and again, we're going to keep the example simple for the sake of discussion. So I'm not going to define very well what I mean by diet, but we can think of having a good or bad diet. What does that effect does that have on your risk of diabetes? And now we want to think through these variables here: genetics, weight, race, physical activity, and religion. Are these variables potentially confounders, effect modifiers? Are they just independent predictors, meaning they are predictive of the outcome, but they're not associated with diet? Okay, they're not confounders. And there's not necessarily one right answer here. The point of this is trying to think through potentially what could each of these variables be. Take a moment to think about it, and then I'll come back with some discussion. First, let's think through part A there, genetics. What do we think? Do we think that, let's think of that top box with the question marks there. Does genetics fit in there? Do we think that genetics is associated with risk of diabetes? I'm going to go ahead and say, let's say it probably is. So there might be, genetics might make you more or less likely to develop diabetes. So right there, if we're thinking that genetics is associated with diabetes, it's a predictor of diabetes. Now, let's think about that second arrow. Does it fit the criteria to be a confounder? Do we think that genetics is associated with one's diet? There I'm going to say probably not. I wouldn't think that someone having a good or bad diet or the way they eat is necessarily associated with their genetics. You can make an argument that maybe there might be certain genetics that make you not be able to tolerate eating wheat or dairy or something like that, but this is a weak association and it doesn't exist for that many people, right? It's not very common. So I would think the association between genetics and diet is weak at best, probably non-existent. Okay, so it fits the bill as being a predictor of diabetes, not really as a confounder. Let's think about, could it make sense as an effect modifier? So that bottom box down there with the question marks. Do we think that, say, the effect of a poor diet and the effect that has on your risk of diabetes changes depending on genetics? Well, yeah, that's a reasonable hypothesis, right? A bad diet might be able to be counteracted by having good genes that aren't as sensitive to that bad diet. So through our discussion here, we've thought through that genetics potentially makes sense as an independent predictor, right? Being predictive of diabetes, but not associated with diet, so not a confounder, or potentially an effect modifier. And just as a quick note, almost any variable, no, I shouldn't say that, but many variables you can hypothesize that they may be effect modifiers. And those are things that can be explored numerically or statistically. Now let's think about weight. First, let's try and think about weight as an independent predictor or a confounder. So do we think that, thinking of that top box up there again, right, with the question marks, do we think that weight is associated with risk of diabetes? Yeah, it surely should be. Do we think that weight and diet are associated? I would think, again, they probably should be. Now let's think about the direction of that association. Does diet directly affect your weight, which then in turn affects diabetes? And I would think it probably does. So there we're thinking it's potentially a mediator. Again, diet directly has an effect on your weight, which then has an effect on diabetes. Now as we're working through this, the point is not to get every single one of these correct or in line with what I was thinking. The goal of this exercise is to help you try and think about what makes a variable an effect modifier, what is a confounder or an independent predictor, and so on. So just to try and help you think through some of these ideas. Now let's think about race. Again, trying to think, do we think race is predictive of whether or not someone gets diabetes? I would say quite potentially. There's probably some genetics that come along with it, or certain races may be more or less likely to be diabetic. So there, I'm thinking that race can be predictive of diabetes. Now, trying to think, is it potentially a confounder? Should race be associated with diet? There, I'm going to say, I don't think so. I would think it should probably be a pretty weak association if there at all. Again, there's always extreme examples you can think of where there's some weak association, right? There may be slight difference in diets depending on race, but I would think that that association is weaker. You could make the argument that it's stronger, and that again could be checked numerically with data. We're not building the skills of trying to numerically work through these things. So there, we're thinking that race may be an independent predictor of diabetes. It may be a confounder if you're thinking that race and diet are associated. And of course, it's not a mediator, right? Diet does not directly affect your race. Do we think of it as being an effect modifier? Again, it potentially could be, right? If the effect that diet has on diabetes changes depending on race. Now, let's think about physical activity. Do we think physical activity is going to be predictive of diabetes? I would say probably so, right? Being more active probably reduces your risk of diabetes. Seems to fit the bill as an independent predictor. What about a confounder? Do we think that physical activity and diet are associated? I think you can make the argument either way. I would think people who are more active probably tend to eat healthier. I'd also think that the association might be pretty weak. There might be people who are active but not, I guess what I'm trying to say is the association between physical activity and diet may be strong or may be weak. We could look into that a bit more, or we could explore it in the data as well. But so again, this could make sense as being predictive of diabetes or potentially a confounder if we think physical activity and diet are associated. Or maybe it's an effect modifier, right? The effect that a poor diet has on your risk of diabetes may be changing depending on if you're active or not. And finally, let's think of religion. Do you think that religion should be predictive of diabetes? I would think probably not. Being religious or not, or being of a particular religion should not really be predictive of whether or not you'll develop diabetes. So right there I'm thinking it's not an independent predictor, therefore it cannot be a confounder if it's not associated with the outcome. What about an effect modifier? Can the effect of a poor diet, the effect that a poor diet has on diabetes, change depending on religion? Again, I would think probably not. So there I'm thinking it doesn't really fit the bill as any of these. And again, the point of that was to have an example that helped you see that sometimes variables don't fit in any of these, that religion is probably not predictive of whether or not someone develops diabetes and is not really necessary in the model. And again, you can disagree with some of the things I said. You may be able to make the argument that certain variables are associated when I said I don't think they are, or vice versa. The goal of this is to try and think through what does it mean to be a confounder, what does it mean to be an effect modifier, what does it mean to be an independent predictor, and so on.
Stick around, guys. There's more to see, and please stay safe.